So let's start lecture 2 on refraction. So in this lecture we will discuss about thin lenses. So these are the objectives. So after you complete this lecture, you should be able to use ray diagrams. To find and position of an image, produced by a converging or a diverging lens, and identify whether the image is real or virtual. And you should also be able to solve problems using thin lens equation. You should also be able to calculate the magnification of the lens, describe the positioning of lenses in compound microscopes and refraction telescopes. So let's start with the lenses. So a lens is a transparent object that refracts light rays such that they either converge or diverge to create an image. So a lens that is thicker in the middle than it is at the rim is an example of a converging lens. A lens that is thinner in the middle and at the rim is an example of a diverging lens. For example, so let's take a simple example of the lenses. So a converging lens is made in such a way that you cut off a part of one side of the lens. So you cut off one part of the lens and you bring the same part of other lenses, so one another lens, so a part of the other lens, and try to attach it together. So this is an example of a converging lens. So in simplicity, we can draw it in such a way where you can consider this is the example of a converging lens. A converging lens is thin at the end, thick in the middle. There is another form of lens, so it's called as the diverging lens. So this is an example of a diverging lens. In a diverging lens, it's thick at the end, it's thin in the middle. Right, so that's the difference between a converging and a diverging lens. So how do these lenses in general work? So let's take a simple example of this. So let's take the example of this lens. So a lens is made of two glass pieces. So when you take light passing through a glass piece, for example, let's consider that we have a block of, so we have a glass block. So we have a glass block, so this is glass here, and this is air, and this is air. So if you look at it closely, and let's say if there is a light ray that's going to hit at it at a particular angle. So this light ray, if you consider it in percentage perpendicular to the plane, so if you consider it perpendicular to the plane, so this is the perpendicular to the plane, then it makes an angle. So originally this would have gone straight down, but it would not go straight down, so rather it would bend. The reason mainly is because, so which way will this bend? Notice that it's going from a rarer medium to a denser medium. So it's going from air into glass, so it bends towards the normal. So notice that this is the normal. So notice that this is the normal here. So it means that it has to bend towards the normal than it usually is. So what will happen here is this particular light ray will bend towards the normal this way. Now it is bending towards the normal and it hits another point on the glass. So it's bending and hitting another point on the glass. And on the bottom part of this glass, again you have a glass and air barrier. So glass and air. Now this time when you draw the normal, notice that it's going from glass into air. So which means it's going to refract in such a way that it actually refracts away from the normal. But when this time it refracts away from the normal, if you notice the original light ray that came through, because it's traveling in the air, the light ray that comes out of this should be parallel to the original light ray because it's still traveling in the air. So what happens here is it bends in such a way that it actually travels parallel to the original light ray that came in. So this is how light actually travels through a glass piece. So this is how light actually travels through a glass piece. Now let's consider the same exact phenomena, and let's consider this phenomena in a different version of how the light would look like. For example, let's say rather than having a rectangular block, let's say I had a block that looks somewhat like a trapezoidal shape. Let's consider this is the block that I am looking at, and let's say there is a light ray that's going to come straight right here. Now notice that here the normal is at an angle. So this is the normal. So it's still gonna bend towards the normal than it originally was. So this is the original light ray's trajectory. So it has to bend towards the normal. So when it bends towards the normal, it bends towards the normal and hits the other glass piece. So it hits and bends the glass piece this way. Now when it hits and bends again, now what will happen again? At this point again, it has to go away from the normal, but this time this is the normal. So notice that this is the normal. So which means that the light ray that was originally going this way, so the originally going this way, now will bend away from the normal. So which means that it has to bend right away from the normal in this direction. So it has to make an angle. So this time it would go in the path of the original light ray. So this time now it goes this way. So there are two angles that we are looking at. So the first angle is this angle. So this angle is the angle of refraction, and this angle is the angle of incidence. Notice that there are two refraction angles. This is refraction angle 1, and there is one another refraction angle right here. So this at the same angle it will hit the other one as well. So which means that this angle between the ray and the glass piece will also be the second incident angle. So I2, this is I1, and this becomes theta R2. To simplify this, we only use both two angles. So this angle and this angle. So these angles here, I'm sorry, this is not the angle. So this is the angle. So we use this angle, incidence angle, and this angle here, the larger angle here, is called as theta E. So remember that theta I represents the incident angle. Theta E here represents the emergent angle. So this ray, the first ray, is called as the incident ray, and the light ray that goes outside, comes through the glass piece and comes outside, is called as the emergent ray. Now the deflection in terms of the wave is not that is very high when you look at it in the large format. As the thickness of this length, so the thickness of this lens decreases. So if this thickness decreases, if the t is so small, then the bend is, so the actual bend inside. So remember that this bend, I am talking about this angle exactly. So this bend angle is negligible. So because this bend angle is negligible, so we can say that it goes nearly as a straight line in the glass piece. Right, it goes nearly as a straight line in the glass piece. So that's what we do here is when we take the entire system, so we neglect these two small angles. So the two small angles that we have here, so we neglect these two small angles, and what we do here in the lens is that the moment the ray touches the lens, it actually bends towards the normal, towards the surface. in this side, in this way. So we do not actually represent the small internal deviation inside the lens, and we write it directly. So this is the lens. That's the reason why this is called as a converging lens. Why is that a converging lens? Notice that all the rays that are passing through the lens will always end up converging at a single point. So they all end up converging at a single point. The point at which they converge is called as the focal point. So the point at which they converge is called as the focal point, and the length from the center of the lens at the point, the distance of the focal point from the center of the lens is called as the focal length. So remember the 2 months. Focal point is the point at which all the light rays converge, and the distance of the focal point from the center of the lens is called as the focal length. So those are the two things. So this is why converging lenses end up converging the original wave. So the light ray actually ends up converging into one single point, and this is the principle they end up using. So the other cases, if you take the exact reverse of this, for example, when you take the exact ray, notice that the light ray that is coming here ends up going towards inside, so this way. So when you look at it in the macro case, so if you consider the macro case, so if you look at the macro case, the light ray will end up bending towards this way. What if you flip the structure? If you look at the diverging lenses, if you look at a diverging lens, and notice that the split here, so split it here and notice this half of the lens. Notice that it's the exact opposite or the reverse of the original lens. So what will happen is that we can take this entire diagram, the same diagram here, so we can take the same diagram and flip it completely. So what is happening here? So let me take out the names. So here also the light ray that is coming in. So let's consider the light ray. So let's consider this is the light ray that comes in. When it hits the lens, again it refracts and ends up refracting here as well. So again here this will be the incident ray. So here this is the incident ray, and this is the emergent ray, and this is the incidence angle, and this is the emergent angle. And there are small deviations when this thickness is small. So when t is small, so it results in negligible angle deviation. So what we can do here, notice this way, here the light rays are not going inward, they are actually going away from the inverter. So for example, if you consider this as the axis, so if you consider this as the lens axis, it's actually going away from the lens. So this is where the center, so it's going away from the center. So that's why when you draw an actual case of so when you draw the actual case of a diverging lens, so when you draw the diverging lens diagram, so the light rays that are coming in will hit the lens and they do not converge, they rather diverge, right? So they hit the lens and they diverge. So that's the reason why it's called as a diverging lens. So this type of lens is a diverging lens, because it's thick at the end, so which means that, remember that the light ray will always bend towards the thicker side. So if you take a converging lens, in a converging lens it bends towards the thicker side, so whichever is the thicker side it bends towards that side. So here also the same reason, it bends towards the thicker side, but the thicker side is away from the middle, so which means that it diverges its light rays. But any light ray that's traveling through the center will come straight through, so there is no divergence in the center because there is equal length or equal thickness at this point. So but on the edges there is much more difference there. So this is the reason why you have a diverging lens and a converging lens. So a converging lens ends up diverging, so a converging lens ends up forming a single point. But how do you do it for a diverging lens? In a diverging lens we draw the lines that are diverging backward, so we end the points drawing them backward and they intersect at that point, so that point is called as the focal point. Right? So that point is always the focal point, and that length is called as the focal length. Now the definition stays the same, still the converging factor is virtual convergence but not actual convergence, because in a diverging lens they never converge. So now this is the example here and how to calculate the focal length. Now when we draw ray diagrams of thin lenses, it is easy to, we use a system that identify the image height and location. So first one, when you will draw a parallel ray. So what is the first rule of drawing the reference rays? There are three rays that you are going to draw. One is the parallel ray, central ray and the focal ray. So let me draw a diagram so that it becomes easier to understand this. So you actually don't need to draw the actual lens every single time. You can just draw it as a single line. I already told you that it doesn't matter because it doesn't make sense. So consider that this is the lens. So for our understanding, let's consider that this is a, so when we draw this, if you draw the arrows like this, so if we draw the arrows like this, we are going to consider this to be a converging lens. Which means there are edges at the end and it is thick in the middle. So when you draw the rays, for example, so every time you draw, you're going to draw mainly two lines. One is the perpendicular axis. This perpendicular axis actually holds the lens. So this is the one which holds the lens, and this here is called as the center of the lens. It's called the center of the lens, and we have 2 points, the focus on either side. Notice that there are 2 lenses, so there you get 2 foci, and there is another point that is 2 times the focus. We already know this. This is called as C. So C is the center of curvature, and F here is the focal point. So let's consider the C here. So what are the 3 rays that, so, and this axis, this is called as the principal axis, and this axis is called as the lens axis. So these are the main ones that we end up drawing, and this is the basic skeleton structure when you draw the ray diagram. Now if you have an object at a certain point, for example if this is the object, the distance of the object from the center of the lens is called P, and for example let's consider the image forms right somewhere here, and the distance between the center and the image is called Q, right? So P here and Q here. So this is the common skeleton structure of a ray diagram for a converging lens. Now let's draw the actual ray diagram itself. So what are the characteristics of converging lenses? Converging lenses always produce real or virtual images. They can produce both real and virtual. So when the image is produced by a converging lens, so then if it generally is reverse and inverted when the object is on the other outside the focal point. So if you have the object outside the focal point, then the image produced, so outside the focal point, then it is real and inverted. Inside the focal point, it is virtual and upright, and at the focal point there is no image formation. So remember these 3 points. If it's outside the focal point, it's real image and inverted image. If it's inside the focal point, the image that you end up with is virtual and upright, and at focal point there is no image formation. So this is the main reason to remember focal point. So focal point is important because at that focal point there is no formation of the image, and this image ends up being a point image. So you only see a single point, right? So that's the idea behind this. Now, so let's try and draw the lens ray diagram. So I'm going to show you the exact method of how to draw the ray diagrams. Because the reason I'm showing you this is because this is one of the lab assignments that you're going to end up doing. So try this so that you know what you all need is, one, you need a scale and you need a pencil. That's the only 2 things that you end up needing in this entire part. So draw a horizontal line first, and then pick any single point in the middle. So for example, let me consider that this point is here, and draw a vertical line at a 90-degree angle. So this is the line. So draw 2 arrowheads that are pointing outward. So when the arrowheads are outward, so let me write it down here. So when the arrowheads are outward, it means it's a converging lens. When the arrowheads are pointed inward, so it means it's a diverging lens. So we don't need to draw the lens diagram every single time because you don't need the actual lens every single time. Just need to know that how to draw the actual, how to draw the arrows. So if you know the arrows, it becomes easier to draw. Now, so the first thing you want to do is, using the point that you have chosen in the middle point, midpoint, at an equal length on both sides, draw the focal point. So let's consider that this is about 4 centimeters here. So 4 centimeters each on each side, and then another 4 centimeters from that point. Right. So the first point that you draw is the focus, and the second point is the center of curvature. You don't need to write center every single time. You can write 2f. So the other name for center is also 2f. Right, 2f. So the side where you draw the object, write it as f1. The side where you have the image, write it as f2. So right, or you can just leave it as f1, f. You don't need to actually worry about it. Next, let's draw the actual object. So there are 3 main things to remember. First is, where are the images being formed. So if it is outside the focal point, then you get a real and inverted image. So let me write it this way. So this is the object position, and this is the image nature. So let me write it this way, image nature. If it's outside the focus, it's real and inverted. If it is inside the focus, so if it is inside the focal point, then the image is virtual and upright. then at focus there is no image formation. So at focus there is no image formation. So remember these 3 points. Now let's go back to the lens diagram. So let's start with a diagram. Let's say I'm going to draw an object of 2 centimeters. So there are 3 main rays that you are going to end up drawing. First ray is the ray passing through the center. So this is the top edge and the ray center, right, and pass a line that passes through both the points. Next ray draw a parallel line from the top edge until the lens and draw a line from there passing through the focus. So from that point and the focus, draw a line, and finally draw a line passing through the focus on the object side. Until the lens, and at the lens draw a parallel line. Draw a parallel line. Now if you draw it according to the length properly, then you should be able to get a single point. So that single point itself describes your final answer. So let me draw the original line, the central line again. So notice the intersection point. So that intersection point, so draw a line at the intersection point. This line represents the image and this is the object, and this is the image. So there are 3 rays. The first ray is draw a line directly passing through the center of the lens. The second line is to draw a line parallel to, so first draw a line parallel to directly to the lens, and then from there draw a line passing through the focus. And the third line is draw it pass through the focus in the object side until the lens, and at the lens draw a parallel line. So and all of them will converge at a single point. That converged point becomes your image. So this is how you can draw the lens diagram for a given quantity. So this length between the object center at the lens center and the object is P, and this length between the lens and the image is Q. Right? So this is the way we draw a lens diagram. So once you understand how to draw the lens diagram, it becomes much easier. So I'm going to draw another one, but I'm going to take another example. So I'm not going to draw the exact length. So this here, so according to here, so we can draw based on what we see here. So let me draw the object with red, and let me draw the image with green. So here we can conclude that when you draw the object between the center of curvature and the focal length, then the image is real, it's also inverted, and it's also enlarged. Notice that the image is actually larger than the object. So what you see physically is also what you end up getting. So it's enlarged. So this is the idea here. So it is real, inverted, and enlarged. So this is the first case when you have the object between the center of curvature and the focal length. Now let's draw the second lens diagram where we try to draw the object beyond the center of curvature. So second diagram is beyond the center of curvature. Again, so the first rule is to draw a horizontal line and choose any center point. So at that center point, draw a vertical line. So again, first put the arrows so that you know it's a converging lens. Next, choose the actual length. So remember that this length should be uniform. If you don't draw the length uniformly, then it will create problems. So 4 centimeters on each side. You can choose any length, but make sure that you choose the same length on both sides. So here I am choosing 4 centimeter focal length. So here also 4 centimeters, and then another 4 centimeters, that gives you the center of curvature. Center of curvature. So this is the center of curvature, focal length, the focal length, center of curvature. Now, so we want to draw it beyond the center of curvature. So let's say I'm going to choose some length here. So here we are not doing anything specifically as per length. So let's choose some length. Let's say I'm choosing the object of 2 centimeters. So beyond the center of curvature. So remember the 3 lines. The first line is a line that passes through the center of the lens. So to pass through the center of the lens. The second line is to pass a straight line and then pass it through the focus. Next, draw a line passing through the focus this time. And then draw a parallel line there. So the intersection point is where you end up getting the image. This is the image and this is the object. So there is the object and here is the image. So notice that if you look at the actual image here, so when you draw it beyond the center of curvature, so the first thing we notice is it's still a real image, meaning that it's on the opposite side, right? And it's also inverted and it's also diminished this time. The reason it's diminished is because we have drawn the length beyond the center of curvature. So this is the idea behind the lens diagrams. So if you remember the 3 lines, then you can draw the lens diagrams. Now, so what I want you to do is take a scale and a pencil and try to draw these 3 diagrams. So first at the center of curvature and at the focus. So try these 2 diagrams and see if you can try to pass through them. Right? So you don't need to draw at focus. So just try at the center of curvature. So pause the video right here and try to draw this diagram and try to see where you would get the ray diagram at the center of curvature. So now let's try two more cases at focal length and inside the focal length. So again, the same rule again here. So first draw a horizontal line. So choose a point and draw the vertical line. So again, represent that it's a converging lens, and then draw the focal point. So for example, here I am taking a focal length of 4 centimeters. So I am taking a focal length of 4 centimeters. So now we want to draw. So this is F, C, C, F and C. So now we want to draw at the focal point. So let's say at the focal point exactly, we have an object that is about 2 centimeters high. So here, so what we want to do now is again use the same 3 rules. So first thing is pass a line straight through the center from the object. Next, this is the first ray. Second ray is to draw a parallel line. And then pass it through the focus. If you notice that these 2 lines, this line and this line, these 2 are parallel to each other. We cannot draw the third line because it's on the focus itself, so we cannot draw the third line. The question comes back, then what's the point, where will you get an image? So this is the point that I was trying to make before. When you draw the object at the focus, there is no image formation. So because these lines extend infinity, so the image forms at infinity. So because there is no image at infinity anywhere, so we will never get an image. So that's why there is no image formation when you keep the object at the focal point. The next one is inside the focal point. So inside the focal point. So again the same rule. So draw a horizontal line and draw a vertical line. So a converging lens representation. Next, choose the focal length. So I am choosing 4. So I'm choosing 4 here. Now let's consider an object inside the focal point. So let's say somewhere here. So it's not exactly. I'm going to choose a small object because I don't want the diagram to get too big. You will know why it gets too big. So this is the object. Now what are the 3? So remember, this is the focus, center of curvature. So focus, center of curvature. Now we want to know the first line is, remember, to draw directly through the center. So object and center. So draw a line passing through the object and through the center, and try to extend it on both sides. You will understand why you will have to extend it on both sides. And the next line is to draw a parallel line through from the object center and pass it through the focus. So pass it through the focus. Now if you notice that these 2 are actually going away from each other. So if you look at the case here, it's actually going away from each other. So which means that this object will also have the same issue. Let me draw it much simpler. So you just need the actual focus at one side only. So I'm gonna draw a distorted diagram so that you understand it better. So now we have a converging lens here, and let's say we have the object here. So notice that we are drawing it inside focus. So focus, center of curvature, focus. So this is the object. Now let's draw. So the first line is a straight line, and then pass it through the focus. So this time, rather than doing it one side, try to extend it on the other side as well. So you will understand it why. The second line is to draw a line passing through the object and the center of curvature. So when you extend both the lines, you end up getting an intersection point somewhere here. So this is the actual intersection point. So this is the image. But notice that the object and the image are on the same side of the lens. So which means that here, this is not the actual image, this is actually the virtual image. So that's why we represent it as a dashed line. Even the lines that you are drawing in the reverse direction, always represent them as a dashed line. So when you represent them a dashed line, so it represents that it's not an actual image, it's a virtual image. So this is the idea behind the two diagrams. So this is the image. Now notice that when you put inside the focal point, the image is virtual and it is upright and it is also enlarged. If this looks familiar, this is the actual principle for magnifying glasses. So this is the actual principle for magnifying glasses. So this is the reason why magnifying glasses can enlarge an image even though if it's a small image, right? So you use a large convex lens, so a large converging lens, and this converging lens actually enlarges the image to a really high point. Now, so there are two things that we want to know. So there are two main common things that we want to know. So we already knew this from before, so we are going to repeat it again. The first one is the magnification factor. Magnification factor is the height of the image by height of the object. So for when you have outside the focal point, so between, there are three cases where you have different magnification factors. So between the center of curvature and the focus, beyond the center of curvature, and inside the focal point. So this value of magnification factor is generally negative h dash by h. So this value in general, when you take between center of curvature and the focal point, it generally stays, so the modulus of m is always less than 1. Beyond the center of curvature, modulus of m is greater than 1, and inside the center of curvature, modulus of m is greater than 1. So m is much greater than 1 when you take it inside the focal point, because the object becomes so enlarged. So this is the reason for magnification here. So this is how you can end up using a converging lens as a magnifying glass, and how the image forms when you keep it inside the focal point. So next, let's talk about diverging lenses. So diverging lenses, all images are virtual, are generally upright, and always diminished. In whatever the case is, they are always diminished. So let's take the example of a diverging lens, and let's see how to draw the ray diagram or the lens diagram for a diverging lens. So the same rules still apply. So draw a horizontal line first. Then draw a vertical line. So this time draw the arrows inward. So don't draw the arrows outward, draw the arrows inward. So this represents that this is a diverging lens. Now again the same rule. So lay down the focal points. So here I am choosing again the same 4 centimeters focal point. For focal point, center of curvature, focal point, center of curvature. Now let's consider that there is an object between the center of curvature and the focal point. Say somewhere here. Let's consider that this is the object. So again the rule stays the same. This time the rules are a little bit different on how to draw the lines. So the first line, always draw it through the center of curvature, center of the lens. Next, draw a parallel line so this time you cannot pass it through the focus. What you will have to do is align this. So align this point. So align this point here with this focal point. So the focal point on the object side. So this time draw a line like this. So connect the both points and draw a line like this. But this time what you have to do here is to remember that this is a virtual line, so which means that this does not exist actually. So because it diverges, so here it's a diverging factor. So it's a diverging lens. Now we have drawn the line backward. The intersection point that you get, notice this intersection point here. So this intersection point here, that intersection point represents the, so this intersection point represents the image. So this is what you can draw as the point here. There is one another you can draw, but this is these two are more than enough. So just by drawing these two you can end up with what you wanted here. So this small speck is the image. So notice that this image is generally is virtual because both of them are on the same side, and is also upright, and it's also diminished. So what's the difference here between a real and a virtual image? So a real image forms on the opposite side of the lens with the object. so it's on the opposite side. A virtual image forms an image on the same side of the object. So if the object and the lens are on the object and the image are on the same side, then that image is a virtual image. If the object and the lens are on the opposite side, so if the object and the image are on the opposite sides, then that image is a virtual image. Right, so that's the difference between a real image and a virtual image. So diminished and enlarged can be represented by looking at the size, by comparing it with the object. So look at this here. So in comparison with the object, image is smaller, so we write diminished. Right, so this is the idea behind the converging lens and diverging lenses. So there are two lines here. First line is draw a line directly passing through the center of the lens. The second line is draw a straight line, but this time draw a line passing through this focus on the object side and the point at which they intersect with the lens, and draw a straight line and draw a dashed line there. That dashed line with intersects with the line passing through the center. That intersection point is the image. So this is how you can draw the image for a diverging lens. Now, so let's continue with the topic, and let's try to analyze it analytically rather than trying to analyze it graphically. So now let's discuss the thin lens equation. So it's similar to the mirror equation that we talked about. It's exactly the same equation. So it's 1 by p plus 1 by q equal to 1 by f. Remember that the assumption here is that the lens is very thin. So only for very thin lenses it works here. So p here represents the distance from the object to the lens, and q represents the distance from the image to the lens, and f represents the focal length. So next one is the magnification of the lens. Magnification is given by h dash by h, which is given as negative q by p. So this is magnification is image height by the object height. Now to note down the actual values correctly, to make sure that the notifications are the actual values get correctly given, we always have to use this common template for the positives and negative sign. So p is positive when the object is in front of the lens, and it's negative if it's in the back of the lens. Remember that the left is considered as, so whenever you take a lens, the left is considered as the front of the lens and the right is considered as the back of the lens. And q, so q is positive when it is in the back of the lens, the image is in the back of the lens. Q is negative if the image is in the front of the lens. So if it is in the front or the left, so it means it's a negative one. And f is positive for a converging lens and f is negative for a diverging lens. So these are the two things to remember. So let's solve a problem so that it becomes easier. So you have an object is placed 30 centimeters in front of a converging lens, then 12.5 centimeters in front of a diverging lens. Both lenses have a focal length of 10 centimeters. For both cases, find the image distance and the magnification, and they are also asking you to describe the images. Now, so let's take down the problem. Let's note down the data in the problem that's given. So you have the object placement. So P here is 30 centimeters, and so this is P for converging, and P for diverging is 12.5 centimeters. Notice that both of them are in the front of the lens. So because P is positive in both the front, so we can write plus and plus. Next, they have given you the focal length. So F for converging is 10 centimeters, but F for diverging, notice that it's a diverging lens, so F should be negative, so negative 10 centimeters. Now let's take the first case where we consider PC is 30 centimeters and FC is 10. So let's solve it analytically. So first one is the converging lens. So P is given as 30 centimeters and F is given as 10 centimeters. So we know the formula is 1 by P plus 1 by Q equal to 1 by F. So 1 by P is 30 centimeters plus 1 by Q is, so Q is equal to 1 by F is 10. So now 1 by q can be written as 1 by 10 minus 1 by 30. So if you take the LCM, it's 30 and you get 3 minus 1, so that is 2 by 30. So 2 ones, 2 15s. So 1 by q is 1 over 15. So if you take the reciprocal, you get q equal to 15 centimeters. So notice that q is also positive here. Next we want to find the magnification factor m. So we know that it is minus q by p. So minus q is 15 divided by 10. So you get minus 1.5. So the magnification factor is negative 1.5. So this is the magnification factor for the converging lens problem. So here notice that the focal length is 10. So we know that the center of curvature is 2f, which is 20 centimeters. So here the case is beyond the center of curvature. So if you remember from the image nature, we know that beyond center of curvature the image is real, it's inverted, and it's also enlarged. So one way of knowing enlarged is to look at p and q. So one way of looking at it is by the m value. So the m value is negative 1.5. I told you that if modulus of m is greater than 1 here, so it's 1.5. So we can write that it's enlarged. So if m is less than negative 1 or m is greater than 1, then the image is generally enlarged. So one way of knowing whether it's inverted or upright is by knowing the m value. If m value is positive, it's upright. If m value is negative, it's inverted. So that's how you can know whether it is inverted or upright. Now the second condition they have given us is the diverging lens. So in this we have p value that is given as 12.5 and f is negative 10. So again the formula is 1 by p plus 1 by q is equal to 1 by negative 10. So 1 by 12.5 plus 1 by q is equal to 1 by negative 10. So we know that 1 by q becomes 1 by negative 10 minus 1 by 12.5. So when you take the LCM, you get, so take the negative to the top. So you have 10 times 12.5. So on the top you get 12.5 here and 10 here. So cross multiply. So you get negative 12.5, negative 10. So you get negative 22.5 over 10 times 12.5. So if you multiply 10 and 10, if you multiply and divide 10 by 10 and 10, so you get minus 225 by 10 times 125. So you get, so calculate the value. So if you use a calculator, you have 22.5 divided by 125. So that's the value that you end up with. So that value is negative 0.18. So this value is 1 by q. Remember that it's still 1 by q, negative 0.18. So we want q. So q becomes 1 by negative 0.18. So 1 divided by 0.18. So becomes 5.55 centimeters. So if you round it off, you get 5.56. So q is negative 5.56 centimeters. So from this we can calculate the magnification factor, so which is minus q by p. I get minus of minus 5.56 divided by p is 12.5. So if you calculate, you get 5.56 divided by 12.5. So you get plus 0.448. So magnification factor is plus 0.448. So it's less than 1, magnification factor is less than 1, so it is diminished. So the image, so remember that this is a diverging lens, so image is always virtual and upright. And because m is less than 1, it is diminished. So image is diminished as well. So this is how you can solve the problem. Remember the notation. So if P, Q, so P, Q and F, plus and minus. So P is positive if the object is in front of the lens. P is negative if the object is in the back of the lens. Q is positive when the image is in back of the lens, and Q is negative if the image is in the front of the lens. Right, so back can be also be right, front can be left. Right, so F is positive for a converging lens, F is negative for a diverging lens. So this is the nomenclature that we can use. So in some questions it might not mention that it's a converging lens or a diverging lens. So one way of knowing it is if they mention convex and concave. So converging lenses are convex lenses and diverging lenses are concave lenses. One way of remembering convex lenses is to remember the first 5 letters. The first 5 letters in both of them are the same. So converging lenses are convex lenses, diverging lenses are concave lenses. So this is how you can remember the signs, and you can remember the name as well.